Does this situation sound familiar? After a long drive, you finally make it to your local hardware store just to pick up some screws and maybe a few odd ends to complete your unfinished project waiting for you back at home. As you meander through the store, you're overcome with a feeling of elation that you'll soon be on your way and feel the satisfaction of finishing that weekend project. As you make your turn into the hardware aisle, a series of bins filled with an assortment of screws welcomes you. So many to choose. You came in for a basic slotted screw and now find yourself debating a hex head. In a manic split decision, you opt for a box of Torx heads, thinking it will impress all your buddies. Finally, you beat the traffic and make it back to your homestead. Take a deep sigh and start to shuffle through your toolbox, when suddenly, your eyes widen and a sense of paralysis hits you. You don't have the right driver for the Torx screws. This moment calls for the proverbial facepalm, but rest assured, everything will be just fine. Let's start by understanding what all these different screws are and where they came from, and ultimately, how they eventually staged their mark of opulence. Maybe to keep you up at night and lose sleep. No, not at all. The screw, as simple as it appears, is a technology so old that no one can precisely determine who first invented it. The best we've come to an answer, and considered by some, is that the principle was first developed by Archimedes, though it's widely believed that he lifted the idea from the early Egyptians. He realized the screw's helical properties can be converted to a rotational motion that creates linear force. This concept was originally used to pump water in what's called a water screw. Seems simple enough, huh? Let's pivot and get a better understanding of how a screw works exactly. Looking closely at the cross-section of the threads, the basic idea of how a screw works becomes evident. This segment of the screw is a wedge, and when you force something under a wedge, it begins to lift itself upwards. And because this wedge spirals around the shaft, that same force is applied along the length of the entire screw. This basic concept has found applications in land irrigation and even to remove bilge water from ships for centuries. Early iterations were even discovered in the ancient city of Pompeii, in which the ancients used a press to extract oils from olives and juice from grapes. Eventually, the idea of adding a head to the screw and using it as a fastener came to light. This was achieved by applying a force to the screw, which in turn causes the threads to pull upwards. The compression generated could be used to securely bind two objects together. But this concept of using the screw as a fastener didn't really catch wind until a method of mass production was first developed. The first truly modern screw cutting lathe was likely constructed by Jesse Ramsden in 1775. This early variant had a lead screw, slide rest, and change gear mechanism, which are elements carried over and even found in non-CNC lathes used today. This first screw cutting lathe would eventually be used to construct other lathes with even higher accuracy. In fact, some of the finest astronomical, surveying, and navigational instruments of the 18th century were constructed on Ramsden's lathe. By the late 1700s, other examples capable of industrial levels of mass production would follow, but the inventors of these lathes would be overshadowed by Henry Maudslay, whose screw-cutting lathe created in the 1800s would be cited as the first. It's clear Maudslay's was not the first, however, his version did spread worldwide as being the best known. Ironically, this was attributed to his version being equipped with the same elements found in Ramsden's lathe, but in an arrangement practical to use and robust enough for cutting metal. Maudslay's lathe ushered in the breakthrough development of the technology, which could operate at a large scale of industrial production for screws that were interchangeable. Initially, this caused friction surrounding differences in existing standards. A notable example of this happened during the Great Boston Fire of 1872, when fire departments from neighboring regions arrived on scene to assist, only to then realize their fire hose couplings were not compatible with the fire hydrants in Boston, making it virtually impossible to connect their hoses and related equipment. Thereafter, the standardization of thread geometry, including thread angle, pitch, major diameters, pitch diameters, began immediately at the intra-company level, and by the end of the 19th century, it had been carried to the international level when the International Organization for Standardization was set up in 1947. Worldwide, the isometric screw thread is the most commonly used type of general-purpose screw thread. Typically, it's designated with the letter M, which indicates the nominal outer diameter of the metric screw thread in millimeters. For example, an M6 screw has a nominal outer diameter of 6 millimeters. The next question we need to ask ourselves is why can't all these screws use the same head so we don't need all these different screwdrivers? To start, the basic slotted or flathead screw was probably the first used since it was the easiest and cheapest to manufacture. But it only really works best when driving the screw manually into the wood. If you're like me, a flathead screwdriver usually slips away from the sides and sometimes even turns off the screw's center axis, usually leading to scratches or damaging the material itself. Or worse yet, cross-threading or damaging the threads. More on this adverse effect later. But with this in mind, there was still room for improvement for the screw to be efficient in a mass production capacity, which led to the next step in the screw's maturation, when Peter Limburner Robertson designed the square or screw-lock screw head. The screw-lock's key feature was a square-shaped socket located on the screw head in which a square protrusion on a tool will slot in. Interestingly, both the tool and the socket have a slight taper, providing two advantages, which have served to popularize this drive. It makes inserting the tool easier and tends to keep the screw on the tool tip without the user needing to hold it. An issue prevalent with the flathead design which caused the driver to deviate off the axis of the screw. The screw locks was even used in the production of the Model T, when Henry Ford found its design could save considerable time in the assembly line. But because of licensing issues on the part of Robertson, Ford realized that the supply of the screws could not be guaranteed and instead chose to limit their use in the production to Ford's Canadian division. Because of his refusal to license the screw locks, widespread adoption in the United States never quite materialized. Instead, the licensed Phillips had gained wider acceptance in the States. The screw locks is still commonplace in Canada, and as patents expired and awareness of their advantage spread, these fasteners have become popular in woodworking and even found a place in general construction. But it wasn't until the Phillips screw came into the picture and really shook things up. The design was the brainchild of John P. Thompson, who, after failing to pique the interest of manufacturers, sold his design to businessman Henry F. Phillips. Subsequently, the Phillips Screw Company was founded and eventually improved the design and promoted the adoption of this new screw. The Phillips Screw Company realized their design was a direct solution to some of the problems associated with slotted screws. More specifically, the difficulty of driving with power tools. Compared to the Phillips screw, the slotted screw lacked the precise alignment required to avoid slippage and damage to the driver, fastener, and adjacent surfaces. This is known as cam out and occurs when a screwdriver slips out of the head of a driven screw once the torque required to turn the screw exceeds a certain amount. Interestingly, there has long been a popular belief that this was a deliberate torque limiting feature of the Phillips design, for the purpose of assembling aluminum aircraft without over-tightening the fasteners. It's likely this was the case since Phillips screws tend to cam out once a certain level of torque is reached. At any rate, the costly shortcomings of the Phillips would eventually be realized by manufacturers as cam out comes at the expense of damaging and even reducing the life of the screw head and driver. But it would be the advent of the hex and torque design that would eventually overshadow the Phillips in certain industries and applications. Though between these two designs, the Torx is much more superior, and thus we'll give it more of our attention. To reduce cam out and extend the life of the related tools, the Torx drive was invented by Bernard F. Ryland for the Camcar Textron Company. Initially, the technology found its genesis in the need to develop better machining techniques and higher precision and torque limiting systems used in automatic screwdrivers. The Torx design accomplished this by increasing the screw's surface area, which greatly reduced the amount of torque applied. This had the effect of preventing over-torquing and slippage, and even worse, potential breakage. Of course, eliminating these issues also extends the life of the tools and fastener, significantly reducing overall manufacturing costs. Let's now compare the hex and torque to better understand the superiority of the Torx design. When looking at it side by side, we can see that they both use the same diameter tool. We can also see that there are 6 points of contact between the tool and the screw itself. As our tool begins to rotate, it's easy to notice that the hex tool contacts the hex screw at a greater radius. This allows the hex tool to apply more torque, but with the same force. However, the plane of contact is not perpendicular to the screw. which means some of the force applied to the rotation of the screwdriver is exerted radially or outwardly. This has a tendency to round off the sides of the female end and split the male end, shortening the life of the tool and screw. Unlike the hex, the angle of contact of the Torx screw is near perpendicular or closer to 90 degrees, which means radial force is much lower and more torque can be applied without damaging the screw. The irony here is that the Torx was developed initially to prevent tampering in electronics, most notably in Apple's first generation of personal computers. This was done by inserting a pin in the screw drive area and requiring a tool with a corresponding hole to drive the fastener. This can also prevent user attempts at turning the screw with a small, flat-bladed screwdriver. That's less of a benefit now given the Torx has proliferated and is pretty common. We all know the frustration of using a flathead screwdriver only to have it pop out on a whim. We also probably have equal amounts of frustration with the Phillips screwdriver camming out. Using a Torx screw and driver, by contrast, is pretty nice. It has a nice snug fit, it doesn't slip out, break, or strip, so long as the high-quality, correct size driver is used. Since their inception, Torx screws have been widely adopted and have had a lot of variations created since.